Good morning, everyone. My name is Muni. Today I will discuss about floating point representation. Let's see what is floating point representation. In computing, floating point representation is the representation that uses a formalic representation of real numbers as an approximation to enable a trade between range and accuracy. As a result, the floating point representation is frequently utilized in systems with very small and extremely large real numbers that demand quick processing needs. Binary numbers can also be expressed in exponential form. The representation of binary integers in exponential form is known as floating point representation. The floating point representation divides the number into two parts. The left side is a signed fixed point integer known as mantism, and the right side is the exponent. Floating point representation can also have a sign with 0 denoting a positive value and 1 denoting as a negative value. The IEEE Institute of Electrical and Electronic Engineers has developed a floating point representation standard. The IEEE specifies two types of formats in floating point representation that are single precision 32-bit and double precision 64-bit. First, I will discuss about single precision floating point representation. The single precision floating point representation, also known as FP32 or float 32, is a computer number format that uses a floating radix point to express a wide dynamic range in number numeric value. The IEEE 754 standard defines a binary 32 as having the following characteristics: 1 bit per sign, 8 bit per exponent, the precision of significant 24 bits, 23 explicitly stored. The structure of single precision floating point representation is as follows. First bit first bit is sign bit and a second bit is exponent and 23 bits as mantism. Let's say we want to convert the decimal number 3.75 into single precision floating point format. First, we determine the sign of the number. Since 3.75 is positive, the sign bit will be 0. Next, we convert the integer part of the number to binary 3. In binary is 11. Then we convert the fractional part of the number to binary 0.75, can be represented as 1 by 2 plus 1 by 4. So in binary it is 0.11. We concatenate the binary values of the integer and fractional parts took from the significand. In this case, the significand is 11.11. Now we need to normalize the significand. We shift the binary point to the left until the leftmost bit is 1 and increment the exponent accordingly. In this case, we shift the binary point to two places to the left to get 1.111 and increment the exponent to get 2. Finally, we add the bias to the exponent and convert it into binary. The bias for single precision floating format is 127. We add 127 to get 129, which in binary is 1601. Putting it all together, the single precision floating point representation of 3.75 is 0, 16 zeros, 4 ones and 20 zeros. The leftmost bit represents the sign 0 for positive. The next 8 bit represents the exponent 1, 6 zeros, 1 in binary equal to 129 in decimal. Minus the bias of 127 gives us an exponent and the remaining 23 bits represent as the significand. Let's see double precision floating point representation. The double precision floating point representation, also known as FP64 or float 64, is a computer number format that uses a floating radix point to express a wide dynamic range of numeric values. The IEEE 754 standard defines a binary 64 as having the following characteristic as same as single precision, but values is different. 1 bit for sign, 11 bit for exponent. The precision of significant is 53 bits and 52 explicitly stored. The structure of double precision floating point representation is as follows. 1 bit is sign and 11 bit is exponent and 52 bit is mantissa. Let's say we want to convert the decimal number 0.1 into double precision floating point format. First, we determine the sign of the number. Since 0.1 is positive, the sign bit will be 0. Next, we convert the number to binary. One way to do this is to use the method of multiplying by 2 and keeping track of the integer part. And the fractional part separately multiplying 0.1 by 2 gives 0.2 with an integer part of 0 and a fractional part of 0.2. We keep multiplying the fractional part by 2 and keeping track of the integer part until we get a binary representation with enough significant digits. After 4 iterations, we get 0.1 equal to 2 equal to 0. And 0.2 into 2 equal to 0.4. In this, integer part is 0 and fractional part is 0.4. 0.4 into 2 equal to 0.8. In this, integer part is 0 and fractional part is 0.8. In 0 point multiply with 2 equal to 1.6. In this, integer part is 1 and fractional part is 0.6. So the binary representation of 0.1 is 0.0001111 and repeating the values. So the binary representation of 0.1 is as follows. Thank you.